In this video, we're going to look at 3D moment of a force using the position vector method. And in the position vector, for what we're going to do, you will see this formula that says M for moment equals R times F. Now, R will represent the position of the point where the force itself acts, and F represents the force that is applied. Now, the moment measures the rotational effect of the force about a point. Now, when we do 2D moment of a force, it's simply force times perpendicular distance, and it's going to be a similar sort of convention that we follow. So this method, which is can also call it the cross product method, I'm going to set this out as a 3x3 matrix, and what we will have is the determinant of I, J, and K. So for our position vectors then, so for R we have 2I plus 3J plus 1K. So we're just gonna simply write the coefficient of I, J, and K. So we'll have 2, 3, and 1. And then for the force, you can see here we have 4, -2, and 5, so we simply write that in the same order for -2 and 5. So what's the unknown here? If you notice at the top where we have I, J, and K, we don't know those coefficients, so we're going to work out those coefficients, which is X, Y, and Z values. So let's do that now. So starting with the I component, in the column where we have the I, I'm just going to highlight that. So going down like that and going across like that. And what we're left with for the I is just what you see in the second row, 3, 1, and in the third row, -2, 5. So that's the matrix that now comes down to a 2x2 matrix that we're going to find the determinant for. So just for clarity, I'll just write out that matrix for you. So for the I component, we're left with 3, 1, -2, 5. And we're going to find the determinant of that. Now, how we find the determinant, we're just going to multiply the leading determinant, which is coming from top left, so these two, 3 and 5. So that's what we multiply now. So for I, we do 3 multiplied by 5, and then we're going to subtract from that the multiplication of the other two, which is our non-leading. So we multiply these two now, going across with the -2 and the 1. So we have 1 multiplied by -2 here, and that leaves us with 5 times 3, 15, and these two are essentially negative, so -1 times -2, that's going to give us 2. So what we're left with is 15 and plus 2. So this gives us 17I. So that's the I component done. So let's move on now to finding the J component. Now I'm just going to clear this so you can see the same process repeated. Okay, so let's go ahead and find the J component now. So for the J component, we're going to go back to our 3x3 matrix, and we're just going to highlight the row with the J and the column with the J. So of course the row with J is the top right there, so those will be eliminated. And then the column with J is this one here. So how we set up this now is to eliminate those elements which are contained in the same row as J and the same column as J. So let's write out the J components now. So then that would leave us with 2, 4. So that's in the first column. And then 1 and 5 in the last column. And it's the same order that we multiply these in. So for the leading, it's going to be the 2 multiplied by 5. And then the non-leading, it's going to be the 4 multiplied by 1. Now, very importantly, for this component, we have to start off with -J. And this is just going into something else to do with matrices, and I'll get into a full video on that just to explain this concept here. So we start off with minus j, and then we do the same multiplication as we did previously. So we'll have leading, which is 2 multiplied by 5, and minus non-leading, which is 1 multiplied by 4. And this gives us with 10 take 4. So we have a negative j there. So this leaves us with negative 6j. And as I said, I'll get into a video on why we start there with a negative j, but that will be on a matrices topic. Okay, so we have one more component now. And remember, what we're doing is this here. We're finding r times f, which is representing our force times perpendicular distance, and that gives us our moment. Okay, so let's go ahead now and find the k components. So for the k components, once again, we're going to cross out the elements in the same column and the same row as the k is. So again, all of what's up top would be crossed out, and all of this bit here would be crossed out as well. So we're left with 2, 3, 4, negative 2, and we do the same thing where we multiply the leading, which is coming from top left to bottom right, by the non-leading bottom left to top right. So that would give us this here. So let's write it up properly. So k components. So that's just leaving 2, 3, 4, and negative 2. And what we are going to do is the same thing. So k would be multiplied by, so that's 2 times negative 2. So 2 multiplied by negative 2. And subtract 3 times 4. So 3 times 4 subtracted. So 2 times negative 2, that gives us negative 4, minus 3 times 4, which is 12. So that's 2 negatives there. So then what we have is k as negative 16k. So that's our k component. Now what we have to do next is to just write down the moment, the vector that represents the moment, using all these components. So let me just clear the screen and we do that properly. So we have m equals, so m for moment, and we're going to write down the result of r times f that we just did. The component that we got for I was 17, so we write 17i. The component for j was negative 6j, and the component for k was negative 16k. And if it's moment, our unit would be Newton meters, and this would represent our final answer. Now in the next video, we're going to take this a step further and have a look at moment about an axis. So I'll see you in the next video.